Welcome, everybody. It is an immense pleasure for me to welcome you to this special colloquium inserted in the webinar series of the graduate program in physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the microphone and camera turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless otherwise requested by the speaker. The questions can be asked using the chat, both in this virtual room and in the YouTube. Today, we have the great honor to listen to Professor Takaaki Kajita, who was awarded with the 2015 Nobel Prize in Physics, together with Arthur Bruce McDonald, for the discovery of neutrino oscillations, which shows that neutrinos have mass. Professor Takaaki Kajita was born in Saitama, Japan. He studied in Saitama University and at the University of Tokyo, where he received his doctorate in 1986, under the supervision of the future Nobel laureate Masatoshi Koshiba. Since 1988, he is affiliated with the Institute for Cosmic Ray Research, the University of Tokyo, and in 2008, he became its director. Since 2007, he is a principal investigator of the Institute for the Physics and Mathematics of the Universe in Tokyo. On October 2020, he became the president of the Science Council of Japan. Presently, our special guest is professor at the University of Tokyo, Kashiwa, Japan. Apart from the Nobel Prize in Physics, Professor Kajita research has been honored with various other prizes, recognitions, including the Asahi Prize in 1988, the Bruno Rossi Prize in 1989, the Nishina Memorial Prize in 1999, the Panofsky Prize in 2002, Japan Academy Prize in 2012, and the Fundamental Physics Prize in 2016. Neutrino oscillations and small neutrino mass is what Professor Kajita will tell us about today, and I should not make you wait longer to listen to him. Professor Kajita, thank you very much once again for having accepted our invitation. From this moment on, the audience is yours.
Okay, well, thank you very much. And thank you very much for the very kind introduction. And today, I want to talk about neutrino oscillations and small neutrino mass. Now, you see a photo in this slide, and this is the super Camiocanda detector. And we have been studying neutrinos with this detector. So today, I'm going to talk about our studies in super Camiocanda. Okay, this is the outline of this talk. First, I have a brief introduction on neutrinos. Then, I'd like to start our activities in Kamioka. And before Super Camiocanda, there was Camiocanda Experiment. Therefore, I'm going to talk about the Camiocanda Experiment first. Then I want to move on to the discovery of neutrino oscillations in Super Camiocanda. And, well, actually, I forgot to write down. And in addition, I'm going to talk about the solar neutrino oscillation discovery. And then I want to move on to the importance of small neutrino mass. And I want to summarize. Okay, what are neutrinos? Well, neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons without electric charge. In fact, this feature has a profound impact to the property of neutrinos, and neutrinos can easily pass through even the Earth. But fortunately, they can interact with matter very rarely. Therefore, we can study neutrinos. Now, one more page. Neutrinos, like the other particles, have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And these neutrinos are listed in the bottom of this table. And in the very successful standard model of particle physics, neutrinos are assumed to have no mass. However, I have to say that physicists have been asking neutrinos really have no mass. Now, the next question is, how can we study neutrinos? Well, first of all, we can never see neutrinos themselves. Therefore, we have to observe very rare neutrino interactions. And in this case, typically, a charged particle is emitted. Then, of course, we have various ways to detect this charged particle. And in our case, the nucleus is an water nucleus. And therefore, we use actually water. And if a charged particle propagates in the water, photons, Cherenkov photons are emitted. And therefore, we detect these Cherenkov photons by photomultiplier tubes. So this way, we observe neutrino interactions, and therefore we study neutrinos. Now, I'd like to move on to the early days of our studies in Kamioka. Well, let me mention about the motivation of the original Camiocanda experiment. In the 1970s, grand unified theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. Well, certainly the idea of grand unified theories was very appealing, and also the prediction of proton decay was very fascinating. Therefore, several proton decay experiments began in the early 1980s, and one of them was Camiocanda. And here I show the sketch of the Camiocanda experiment. It is a 3 kiloton water detector. We constructed 16 meter in diameter and 60 meter in height, a water tank in 1,000 meter underground. And in the inner surface of the detector, the tank, we put photomultiplier tubes to observe Cherenkov photons. In fact, if a proton in this water tank decays, then typically 2 or 3 charged particles is emitted. Then these particles emit Cherenkov photons, and then these photomultiplier tubes detect these Cherenkov photons. So that way, we wanted to observe proton decays. And here, I show a photo that we took during the construction of the Camiocanda experiment. And in the middle, you can see Professor Kashiwa, and he received Nobel Prize in Physics in 2002 with this, with the experiment, with the neutrino detection in this experiment. And well, in fact, these are the people who constructed the Camiocanda experiment. And behind Professor Kashiwa, there are 4 young students. They were the main people who really constructed the Camiocanda experiment. And here I show you the photo of the Camiocanda experiment during the construction. In order to install the photomultiplier tubes into the Camiocanda tank, we decided to use these plastic boards. Now, of course, we wanted to observe proton decays, but unfortunately, proton's lifetime is in fact much longer than expected or predicted by the grand unified theories in the 70s. So we didn't observe proton decays. Instead, we observed background events to the proton decay surge that were neutrino interactions in the Camiocanda tank. And these neutrinos are created by cosmic ray interactions in the air. The cosmic ray particles entering into the atmosphere, they interact with air nucleus, then typically pions are produced, and these pions are unstable, therefore decay to a muon, then to electron. So during this decay chain, neutrinos are created. And most of these neutrinos simply pass through the Earth, but some of them interact in the Camiocanda detector. Now, I want to discuss our studies around 1986. Well, that was already 3 years after the start of the Camiocanda experiment, and we still wanted to observe proton decays. However, at that time, no evidence for proton decays, but we had accumulated a substantial number of neutrino background events. Therefore, we began to think that maybe there are proton decay events among the so-called neutrino background events. Therefore, we think we have to improve the analysis in order to better separate proton decay signals and neutrino backgrounds. So, in 1986, we developed new software to improve the proton decay analysis. And of course, if we develop new software, we have to test this software. And in fact, we carried out various tests. And finally, as the final test, the neutrino type was studied for the atmospheric neutrino events. Then we found that the number of muon neutrino events was much fewer than expected. By the way, in the right side, I show a typical event pattern of muon-neutrino interaction in Camiocanda. Here, the cylindrical detector is open to flat. And in this figure, each circle represents the photomultiplier signal observed in Camiocanda. So we see this kind of ring pattern for typical neutrino interactions. Anyway, we found that the number of muon neutrino events was much fewer than expected. Of course, this was the moment that we were testing the new software, and the software told us that the result is not as expected. So we thought that this is very likely that there are some mistakes somewhere in the data analysis, or maybe in the data reduction or somewhere. And therefore, it was clear that there's some problem. So we started various studies to find out mistakes. But in fact, we tried to find out our mistake, and we spent about a year, but still we were unable to find any serious mistakes. So after about 1 year of studies, we concluded that the mu neutrino deficit cannot be due to any major problem in the data analysis nor the simulation. So we decided to publish our data. And here in the middle, we showed the essence of the paper we published in 1988. We simply counted the number of mu neutrino events. That was 80-some number, while the expected number was 140-some. So clearly there is a deficit. We also counted the number of electron neutrino events. They were, well, and compared with the expectation. And for the electron neutrino events, the data and simulation agreed reasonably well. So this was the Camiocanda paper published in '88. Well, okay. This paper essentially reported data only, and we had no clear idea what was the cause of the deficit. But I was most excited with the data. And therefore, I changed my research completely from the proton decay searches to neutrino studies to know what is happening in neutrinos. But of course, with the data presented in presented in '88, we are unable to find out the cause of the deficit. But from the beginning of the, well, from that time on, we have been thinking that maybe the cause was due to neutrino oscillations. Well, according to the neutrino oscillation theory, which was predicted by Maki, Nakagawa, Sakata, and Pontecorvo, if neutrinos have mass, neutrinos change their type from one type to the other. For example, in this figure, if a neutrino is created at this point 0, then begin to propagate to the right, then at some point, the probability that mu neutrino to remain mu neutrino goes down. But if these particles continue to propagate to the right, then this probability come back to unity, then go down, go back to unity, go down, and so on. And when mu neutrino disappeared at that time, at that moment, the tau neutrino is appearing. So this is the neutrino oscillation prediction. And if this is happening, then naturally we can explain the deficit of mu neutrinos. But of course, there were various possibilities to explain the deficit of mu neutrinos. Therefore, we thought that we have to find a way to know if the deficit is due to neutrino oscillations or by some other reasons. And for this, we thought this way. I said that neutrinos are created by cosmic ray interactions in the atmosphere. Therefore, these neutrinos are created in every place in the atmosphere of the Earth. Therefore, some of these neutrinos are created above us, maybe 10 to 20 kilometers above us. And these neutrinos come to the detector after traveling 10 to 20 kilometers. And since the flight length is only 10 to 20 kilometers, these neutrinos may have no time to oscillate. On the other hand, neutrinos are created in the other side of the Earth. And these neutrinos must propagate inside the Earth before interacting in the Camiocanda detector. And therefore, these neutrinos have to propagate, have to fly long distances. And therefore, these neutrinos may oscillate. So if we think this way, if this is happening, we should observe the up versus down asymmetry of the atomic neutrinos. However, unfortunately, the 3,000-ton Camiocanda detector was too small to observe this kind of effect. Clearly, we needed a much larger detector, and that was the Super Camiocanda. Now, I'd like to move on to the discovery of neutrino oscillations. Well, of course, Super Camiocanda is a much larger version of the original Camiocanda detector. It is a 50,000-ton water Cherenkov detector. It is about 40 meters in diameter and 40 meters in height. And now this is an international collaboration. We have about 190 collaborators from 10 countries. And I want to show you this photo. This photo was taken when we constructed the Super Camiocanda detector in underground. And these people worked together to construct the Super Camiocanda detector. And by the way, I want to also mention that about 80% of these people are physicists, Super Camiocanda collaborators. So in that year, 1995, we physicists worked in underground to construct the Super Camiocanda detector. And the construction work went well. And in January 96, we started filling pure water into the Super Camiocanda tank. And this photo was taken from the top of the Super Camiocanda detector, viewing inside. And you can see the water level. And in fact, the construction finished and this experiment started in April 96. And from the beginning of the experiment, we observed atmospheric neutrinos. This is just one example of the atmospheric neutrino event observed in Super Camiocanda. So we observe these neutrino events every day. About 10 neutrino events in a day is observed. And we studied these neutrino events as a team. And in fact, I think we worked really hard. And in 2 years, we were able to report the first important result from Super Camiocanda. And we reported our result at the Neutrino conference in 98. And here I show you this one of the slides we presented at the conference. Of course, in 98, we didn't use PowerPoint. And therefore, we simply used plastic film. We copied the data to the film and wrote down several comments onto the film, and we presented. But anyway, we think that this slide was very important. In particular, please look at the lower panel. Here, we show the number of muon neutrino events as a function of cosine zenith angle. 1 means downgoing neutrinos, -1 means upward-going neutrinos. And black dots with error bars show the data, and squares with shaded squares show the Monte Carlo predictions. And you can see for downgoing neutrinos, the data and Monte Carlo agreed quite well. But for the upward-going neutrinos, the data showed almost a factor of 2 deficit compared with the Monte Carlo prediction. And this can be quite well explained if we assume neutrino oscillations, namely muon neutrinos created in the other side of the Earth oscillate to tau neutrinos while propagating in the Earth. Therefore, the probability that the muon neutrino stays as muon neutrinos when they interact at the super Camiocanda tank is about 50%. Okay, well, this way we convinced the physics community that neutrinos oscillate. And of course, we reported our result at the conference for physicists. But I think we were extremely fortunate. President Clinton gave a talk at the MIT's 98th commencement. And in fact, his speech is still accessible on YouTube. And therefore, if you are interested in, please visit this URL. Anyway, in the middle of his speech, he mentioned about the super Camiocanda result. And he said, just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. And of course, as the US president, he mentioned the US contribution to the super Camiocanda experiment. Then he came back and said, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So I think we were really honored to hear this kind of speech from the US president on the next day of our discovery announcement. Now, from now on, I would like to briefly discuss the solar neutrino oscillations. Well, of course, the sun generates energy by nuclear fusion processes, and during these processes, many neutrinos are generated. Therefore, if we observe solar neutrinos, we confirm the solar energy generation mechanism. And therefore, the pioneering home-stake solar neutrino experiment started, and in fact observed solar neutrinos for the first time slightly more than half a century ago. However, the event rate was only about 1/3 of the prediction. This was a serious problem, and this problem was confirmed by the subsequent experiments in the 80s and 90s. So this was the solar neutrino problem. Unfortunately, during the 20th century, we didn't have extremely clear idea what was going on. I mean, we didn't have experimental evidence to explain the deficit of solar neutrinos. And then there was the snow experiment. It is a 1,000-ton heavy water detector located extremely deep underground, 2 kilometers from the surface. It was located in Canada. And by using heavy water, they were able to observe electron neutrino flux by the charged current interactions. Mu-E interact with the deuteron, producing E-PP, or they can observe the total neutrino flux by a neutral current interaction. Neutrino interact with the deuteron, producing neutrino PN, and the snow experiment observed the neutron produced by this interaction. Then they found that if they observed the electron neutrino flux, the observed flux was about 1/3 of the prediction. However, if they observed the total neutrino flux, the observed flux was just as expected by the theory. So clearly, this indicates that about 2/3 of the electron neutrinos produced at the center of the sun changed their flavor to mu plus mu tau. And therefore, this was the evidence for solar neutrino oscillations. So this was the story about the second neutrino oscillation discovery. And since there are 3 neutrino flavors or neutrino types, there must be 3 neutrino mixing angles. And therefore, there must be the 3rd neutrino oscillation channel. And in fact, after the discovery of the solar neutrino oscillations, the community's interest was the discovery of the 3rd oscillation channel. And in fact, these oscillations were discovered by long baseline experiments and short baseline reactor neutrino experiments. They are listed here. So these experiments contributed to the discovery of the 3rd neutrino oscillation channel. That was around 2011 to 12. So with these results, the basic structure for 3-flavor neutrino oscillations have been understood. So I think we had really a great progress in recent years in the understanding of neutrinos. Now, I'd like to move on to the importance of small neutrino mass. Well, I mentioned that President Clinton gave a talk and gave a speech at the MIT mentioning about the super Camiocanda result. And you may wonder why neutrino mass is so important. Well, we think the small neutrino mass is very important. And in order to explain, I'd like to show you this slide. Here, I plotted the mass of charged leptons and quarks. There are 3 types of charged leptons and 6 types of quarks. These mass are plotted here. Now, we know the neutrino mass themselves reasonably well. And therefore, I try to plot the neutrino mass in this figure. And then the neutrino mass would be around here. And clearly, you notice that neutrino mass is smaller than the corresponding mass of charged leptons and quarks. And clearly, the neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. So 10 orders of magnitude different. Very small. We believe this is the key to better understand elementary particles and the universe. And of course, if we understand why neutrino mass are so small, then we better understand elementary particles. But we think that neutrino mass is also relevant to the understanding of the universe. And I want to mention why we think so. Here, I simply show a photo of the far universe. We can see many stars and galaxies. And, well, there's one thing we know. These stars and galaxies are made of matter particles. There is no antimatter star or no antimatter galaxy. But if we think about the Big Bang universe, we do not understand why at present we have matter particles. Because during the Big Bang universe, particles and antiparticles are created simultaneously. Therefore, in the Big Bang universe, we naively expect that the number of matter particles and the number of antimatter particles should have been equal. Then, with the universe cooled down, matter particles and the antimatter particles meet and annihilate. Therefore, at present, we do not expect matter particles to remain. In fact, we understand why at present we have matter particles. In Big Bang, I would say that the number of matter particles were 1,000,000,001. On the other hand, number of antimatter particles were 1,000,000,000. They were almost equal. Then, with the universe cooled down, matter particles and antimatter particles meet and annihilate. Therefore, at present, we have this extra one remaining. Excuse me. So, this is our universe. So, this way, we understand why, at present, we have matter particles. However, of course, we have to explain why there was an extra one in the Big Bang universe. And in fact, we do not know why there was extra one in the matter side, matter particles. But we are thinking that neutrinos with very small mass might be the key to understand this big mystery of the matter in the universe. So we think that neutrinos could be the key, but since this is just a possible, one of the possible idea, therefore we have to test experimentally. So we'd like to know if neutrinos are related to the origin of the matter in the universe. Unfortunately, the present-day experiments are not powerful enough to observe this effect. And in fact, we'd like to observe if oscillations of neutrinos and those of antineutrinos are different. Since the present-day experiments are not powerful enough, we need the next generation long baseline experiments with much higher performance neutrino detectors. And in fact, there are two projects going on. One is the DUNE experiment in the United States. Another is the Hyper-Camiocanda experiment in Japan. And since I'm in Japan, therefore, from now on, I'd like to discuss the status of the Hyper-Camiocanda experiment. First of all, Hyper-Camiocanda will be a 190 kiloton water Cherenkov detector, which is approximately 8 times larger than the present Super Camiocanda detector. And furthermore, there is a JPAC accelerator. And at present, this accelerator complex can deliver the proton beam with the beam energy of 0.5 megawatt. And we'd like to improve the intensity to 1.3 megawatt. Therefore, compared with the present T2K experiment, we are going to improve the neutrino intensity, neutrino event rate by a factor of 22. So this would be a big jump compared with the present generation experiment. And because of this huge mass, we have many important research topics in neutrino physics and astrophysics, and also the proton decay search. And the construction started last year, and the experiment will start in 2027. And at present, Hyper-Camiocanda collaboration have more than 400 members from 19 countries. And this is a sensitivity on the CP violation search in DUNE, US, and Hyper-K. And here the sensitivity is plotted as a function of CP phase delta. Of course, the true CP phase is 0. Then, of course, we can never see the CP violation. But for a reasonably large phase space of the CP phase delta, these experiments have a very high sensitivity to confirm the non-zero CP phase in neutrino sector. That should be the major discovery in neutrino oscillations. Furthermore, I just want to mention that because of the huge mass, the Hyper-Camiocanda would have a very high sensitivity to the proton decay search. For example, assuming that proton is going to decay to E plus and pi 0, then after approximately 20 years of the operation, and if the true proton lifetime is approximately 10 to 35 years, then Hyper-Camiocanda will have a 3 sigma discovery potential of the proton decays. And also, well, according to some theories, proton may decay to neutrino plus K plus. Well, certainly Hyper-K can improve the present limit, but for this decay mode, DUNE could be slightly better. Now, I'd like to mention the location of the Hyper-Camiocanda detector. Here in the left upper corner, here is the there is Super Camiocanda detector. Now, Hyper-Camiocanda is going to be built in a separate mountain about 8 kilometers south of the present super Camiocanda. And in fact, the access tunnel will be constructed Okay, so this is a schedule of the hyper-Camiocanda construction. We are in a geosurvey period, and the tunnel construction will start soon, followed by the underground cavity excavation, then tank construction, phototube installation, filling water, and start operation in 2027. At the same time, JPAC intensity will be improved, and also the new near detector will be constructed. And in the JPAC side, the beam will be available in 2027. And finally, this shows the status of the construction at the site. The upper left figure shows the geological survey at the hyper-Camiocanda site. In fact, this is really inside the hyper-Camiocanda cavity. Well, this is going to be, of course, excavated, but this is the place that the excavation will be taken place. And the lower right photo shows the preparation of the entrance yard. So the hyper-Camiocanda entrance tunnel will be excavated at the right side. So clearly, the construction work for hyper-Camiocanda has started. And we are really looking forward to start the experiment in 2027. Okay, let me summarize. Neutrinos are very important for the studies of the universe. Neutrino oscillations and therefore small neutrino mass were discovered by Super Camiocanda in 1998. Small neutrino mass is very important for better understanding of elementary particles. Small neutrino mass might also be the key to understand the fundamental questions of the universe. So we would like to continue contributing to neutrino physics and astrophysics with the next generation experiment, hyper-Camiocanda. And finally, I think it will be great to work together in hyper-Camiocanda with our international colleagues, and hopefully including our Brazilian colleagues. Okay, that's all. Thank you very much.
So thank you, Professor Kajita. So before we continue, it's a tradition here. We will ask everybody to turn on their microphones for a big round of applause in acknowledgement for this excellent webinar. Before we continue, we already have some questions registered. But before, while people are stimulated to write more questions, let me give you an overview of the audience that you have had around this webinars of yours, this international webinar. Let me tell you. So we had more than 100 people when we count together people that are inside this Google meeting room and in YouTube from various different places in Brazil. So all the 5 different regions in Brazil, from west to east, from north to south. So states like Amazonas, Pará, Bahia, Maranhão, Pernambuco, Paraíba, Rio Grande do Norte, Distrito Federal. Rio de Janeiro, Minas Gerais, São Paulo, Espírito Santo, Paraná, Santa Catarina, Rio Grande do Sul. I don't know if you have been to Brazil, but so it really represents, I mean, many, many different places in our country. Obviously, since this webinar has been organized by our graduate program, so we have the undergraduate students, the graduate students, postdocs, teachers, and professors from our graduate program, like Professor Clautal, Macedo, Danilo Ivan Alves, Jaime Urban, Jorge Castineiras. And also, I must say that we have, so Pará is a huge state, by the way, with a big Japanese colony here. So but we have people from Ananindeua, Abaetetuba, Benfica, Castanhal, Capitão Poço, Marabá, and Salinópolis, with also teachers from these places, like Tiago Martins from Unifespa. So I should mention, just to make it registered, so that we have students, teachers, and professors from universities, institutes, and research centers in Brazil. And I would like to mention just some of them to illustrate: Álvaro Nogueira, Carlos Pires, Carlos Frajuca, Emanuele Horazzi, Gustavo Vicente, Elias Shapiro, Zé Ricardo Souza, Júlio Fabres, Kepler Oliveira, Leila Graef, Márcia Begali, Marcos Oliveira, Nelson Studa, Nelson Yokomizo, Paulo Silva, Renato Ângelo, Rodolfo Casana, Rodolfo Lima, Ronald Schella, Sati Skuma Vieis, Valdir Bezerra, and Wilson Zanquim. So I normally do that also to acknowledge these friends that attend this webinar. So, Professor, this is a huge and representative audience from all around Brazil. So thank you very much once again. So let's start. Let's start with the questions then. So the first question comes from Professor Renato Ângelo from University of Paraná. Renato, would you like to make the question yourself, or do you want me to read it for you? Okay, so I'll read it. So he asked, why do neutrinos oscillate? Are these oscillations somehow related to mass superposition? So if you could just give an overview, that would be great. Thank you.
Okay, thank you. Well, certainly the mechanism of the neutrino oscillation is a bit complicated. Certainly, the neutrino flavor state and neutrino mass state do not agree in general. Therefore, there must be some mixing. And in fact, this is the key to understand the neutrino oscillations. And well, I'm afraid to explain more would be a bit too much. I'm sorry.
Okay, Professor. Thank you very much. So the next question comes from Rodolfo Valentim from Unifesp in Diadema. So, Rodolfo, do you want to make the question yourself, or do you want me to read it?
Hi, Professor Kajita. How is the future of neutrino supernova neutrino detections, and what can we learn about it? Okay.
About the supernova neutrino detection in the future. Well, certainly. Well, for example, if a supernova explosion occurred at the center of the galaxy, then in hyper-Camiocanda, we should be able to observe, I don't know the exact number, but typically, approximately 50,000 events in about 10 seconds. So, with this huge number of neutrino event statistics, we would be able to understand the detailed mechanism of the supernova explosion. Well, in fact, the supernova explosion seems to be rather complicated because, well, for example, in order to reproduce this supernova explosion, you definitely need multidimensional simulation of the collapsing star. So clearly, these neutrino data would help understand the supernova explosion.
Okay, okay, thank you so much.
Okay, so thank you, Rodolfo, for your question. Thank you, Professor Kajita, for your answer. So the next question comes from João Paulo da Mata. He wants to make it himself. He's a master's student at the University of Paraíba. So please go ahead, João.
Professor, good night. It was a pleasure to me to see your talk. I have a question about sterile neutrinos.
Mm-hmm.
Do you believe in the existence of sterile neutrino as EV sterile neutrinos or a more heavy type?
Okay, thank you for this question. Well, in fact, personally, I think the experimental evidence for the electron volt sterile neutrinos are still weak. So therefore, I am not believing the sterile neutrinos yet. Clearly, I hope better experiments to be carried out in order to better understand the situation. Improve the situation, I mean. Okay?
Thanks.
Okay, thank you, João, for your question. Thank you, Professor Kajita, for your answer. Now we have a question from Satish Kumar, DH from Unirio. Satish, do you want to make the question yourself?
Yes, thank you, Luis. Thank you, Professor Kajita, for the talk. I have two questions related to the experiment. The first one is about the detector itself. So why do all detectors use pure water? Can't use another type of liquid?
Mm-hmm. Okay, well, about this question, I would say, well, for example, Super Camiocanda contains 50,000 tons of liquid. Then you have to worry about the budget to buy these liquid. However, if you use water, well, you do not need to pay typically. Well, at least in Super Camiocanda, we simply use the water flowing underground. Of course, we purify them, but all the money we need is the money for the purification system. So water is the cheapest. That is the main reason. Another reason is, in order to observe Cherenkov photons, you need to have very transparent medium, and certainly water is very good. So because of these two reasons, main two reasons, we choose water.
That's great. The second question is about, you mentioned there are many channels of neutrino oscillations, right? Have all the channels been measured with equal precision, or some are better measured than the others? Thank you.
Well, thank you for this question. In fact, nowadays, neutrino mixing angles have been rather well measured. However, surprisingly, the accuracy depends on the neutrino mixing angle. And very surprising thing is the least, well, I would say, the most biggest uncertain mixing angle is the angle that is related to the nu tau oscillations. That was the one discovered at the beginning. well, maybe this is too much. Anyway,
okay.
Yeah.
Thank you. Is that because of the short lifetime of tau neutrinos? Thank you. That's it.
Okay, so thank you, Satish, for your questions. Thank you, Professor Kajita, for your answer. Next question comes from Luis Felipe Demetrio. That is he's an undergraduate student at the University of Maringá in the south of Brazil. Luis, do you want to make the question yourself, or do you want me to read it?
Myself, please.
Go ahead.
Hello, Professor. Thanks very much for the talk. And could you please elaborate more on the relation between neutrinos and the matter and the antimatter symmetry problem?
Mm-hmm. Okay, thank you. Well, okay, so first of all, we understand that neutrinos have very small mass. Now, in order to explain the very small mass, you typically need to introduce a very heavy neutrino-like particle. And of course, these neutrino-like very heavy particles are too heavy for us to really observe them at present. But these particles should have existed in the Big Bang, very hot universe. And we believe that these very heavy neutrino-like particles, when they decay to other particles, generated the source for the matter and antimatter asymmetry of the universe. So this way, we think that neutrino physics is related to the understanding of the matter in the universe. Okay?
I see. Thank you very much.
Okay, so thank you, Luis, for your question. Thank you, Professor Kajita, for your answer. So next question, just a minute, comes from Igor Pará from University of Rio Grande do Norte. He's a PhD student there. Igor, do you want to make the question yourself or do you want me to read it? Okay. Then I read it. He has written down, are neutrino Dirac or Majorana particles?
Thank you very much for this very important question. Well, certainly, since I am an experimental physicist, I think that we have to experimentally confirm if neutrinos are Majorana particles. And for this, we think that double beta decay experiments are very, very important. But anyway, we do not know yet. Okay, that is my answer.
Okay, so thank you, Igor, for your question. Thank you, Professor Kajita, for your answer. So next question comes from Emily Costa. She is from University of Pernambuco in the Northeast also. Emily, do you want to make the question yourself?
Yes, thank you. Good night, Professor. Thank you for the talk. My question is, the experiments used to detect and observe neutrinos are all underground, it seems. Why exactly is that? Would it be to avoid other particles' interference?
Yeah,
Exactly
well, yes, thank you for this question. Yes, yeah, I didn't explain. Yeah, but certainly, of course, neutrino interactions are rather rare. Therefore, we have to minimize other backgrounds. And if the detectors are located on the surface, there are cosmic ray backgrounds. And in order to avoid cosmic rays, we go underground, very, very deep underground. And in fact, if we go 1,000 meters underground, then we can reduce the cosmic ray flux by approximately 5 orders of magnitude. So that's a reason.
Okay, I see. Thank you very much.
Okay, thank you, Emily, for your question. Thank you, Professor Kajita, for your answer. So next question comes from Professor Ronald Schellert from Brazilian Center for Physics Research. So Professor Schellert, please go ahead.
Hi, Professor Kajita. I had the pleasure to meet you a couple of years ago in the Canary Islands in the inauguration of the large CTA telescope.
Oh, yeah.
Yeah, I have been following up, the work of our Brazilian colleagues, and I hope that we can increase the amount of young people joining Camiocanda. But I have a practical question about Camiocanda. what is the upper limit in energy which you can you are sensitive to? Let me explain the reason. I am associated to experiments we want to set up in the high Atacama to measure gamma rays, and our lower limit is about 100 GeV. Can we match that with the top energy of Camiocanda? I mean, because that would make a multi-messenger very interesting.
I see. Well, if you talk about the electron neutrinos, I think practically the upper limit would be about several hundred GeV, because above several hundred GeV, the event rate would be very low. Well, as hardware, we can certainly observe even higher energy electron neutrino events, but well, the event rate would be low. And certainly for this kind of physics, hyper-Camiocanda is unfortunately too small. I think we need some other detectors such as ice cube. That is my honest answer to your question.
Okay, so thank you, Professor Shelley, for your question. Thank you, Professor Kajita, for your answer. So next question comes from the northeast of Brazil, so Paraíba, Paulo Silva. Do you want to make the question yourself, Paulo?
Sure, good enough. Dear Professor Kajita, thanks for the nice talk. It was a pleasure for me to see such a great talk. Mine is just a simple question out of curiosity. Why is such a proximity between these two experiments, Super Camiocanda and Hyper Camiocanda? Is there any experimental reason for that, or is just coincidence?
Oh, well, okay. In Super Camiocanda, we think that our main limitation is the number of neutrino interactions. Super Camiocanda is, we are beginning to think that it is too small. So we simply need bigger detector. Therefore, we use the same technology and make Super Camiocanda bigger. That is Hyper Camiocanda.
Oh, yes, but why are they so close to each other?
So close to each other, thank you. Well, okay, thank you. Well, we are going to use the neutrino beam generated by the JPAC accelerator complex. And the beam line is already constructed. And we are going to use the off-axis neutrino beam. Therefore, we do not, these detectors need not be just on the neutrino beam. They are away, several kilometers away from the center of the neutrino beam. Therefore, these two detectors are separated, but they can be exposed to the, essentially to the same beam.
Thank you.
Okay, Paulo, thank you very much for your question. Good to see you. Thank you very much, Professor Kajita, for your answer. So we have a last question that comes from about 5,000 kilometers from where I am, but still from Brazil. It is from Professor Kepler Oliveira from Rio Grande do Sul. Professor Kepler, please go ahead.
Thank you, Professor. My question is about the number of neutrinos. Isn't the data from the Planck satellite enough to show that only 3 and not any larger?
Oh, your question is about the neutrino, number of neutrino flavors.
Yes.
Yeah. Okay. Well, we know that the number of so-called active neutrinos should be 3.
No.
There are several evidences. For example, the LEP experiment at CERN made a measurement on the active neutrinos, and they gave 3. Also, cosmology suggests 3.
Yes.
Yeah.
So isn't it accurate enough to show that it's only 3 and not more? Isn't it accurate enough? The cosmology, for example.
Cosmology, I don't know about the accuracy about the cosmology prediction, but clearly the rep data very strongly suggests 3. Yeah.
Okay. Thank you.
Okay, so thank you, Professor Kepler, for your question. Thank you, Professor Kajita, for your answer. And at this moment, before we close this wonderful event, I would like ask everybody to turn on their microphones once again for a final round of applause in acknowledgement for this, as I said, wonderful, nice session, nice webinar. Thank you very much.
Thank you.